Okay, and let me share my presentation. Okay. All right, so, oh wait, why is it starting at the end? Okay. So this is the 10th recitation, welcome. And today we're gonna be going over these 5 things. We're gonna go over memory hierarchy, and the layout of arrays in memory, and layout of structs in memory, locality, and just a quick introduction to caches. And yeah, so basically we're just building toward learning more about how memory works and how things are passed between the processor and the memory, and how that can be sped up, and how the system decides to store things in memory in order to be able to access them faster. So I have a couple announcements. PA4 has been extended to Thursday until 11:59 p.m. So you guys get an extra 2 days. And I saw that some people still haven't started, so I would recommend getting started as soon as possible. Although I do think that everyone in this recitation right now has probably started. And okay, so let's start with memory hierarchy. And so basically our computers have RAM, random access memory, and RAM comes in two types. So, well, there's multiple types, but these are two of the broader categories. So there's SRAM and there's DRAM. And static RAM is the type of RAM that's used in cache memory, and DRAM is the type of RAM used in main memory. And main memory is just the regular RAM that we have in our computers, but we'll talk more about cache and SRAM as we go on. So I just wanted to have this diagram here to kind of talk about how the CPU communicates with memory. So we've got our main memory here, and we have a bus, which basically it's a bunch of wires that can carry data. And so through this bus, it goes to the I/O bridge, and this is where the input output happens. And from here, there's a system bus, and that goes into this bus interface here. And then from this bus interface, we could put data into registers. And in the CPU, we also have the ALU, the arithmetic logic unit, and that's what performs calculations. So it takes things from the register, does some calculations, returns it, sends it back, and that's basically how CPU and memory communicate. And when we get to the end of this presentation, we'll see that there's another piece that that we'll be talking. There's many pieces in the CPU, but there's another piece that we'll be talking about, which is the cache. And so this is based just like a pyramid that kind of depicts the memory hierarchy. So we have registers. This is the closest to the CPU. So this is where the CPU directly gets things from, or I guess the arithmetic logic unit. And so the CPU gets these from the L1 cache or the L2 cache or L3 cache. It depends on which processor design has been chosen for the specific CPU chip, but it could have any number of caches. And these are what are called SRAM. And then we have the main memory, which is a form of DRAM. And so main memory is basically memory that can, it's memory that, it's also called volatile memory, which means when you turn off the computer, whatever was stored in it goes away. So, and then so that's what our RAM is. It holds temporary things. But the local secondary storage, which is local disks like hard drives and solid state drives, those hold things permanently. So we could put files and other things in those. And then we also have remote secondary storage, which is like web servers or something if you were to store something on the cloud, Google Drive, something like that. And so we'll get into, we'll talk more about caches and stuff later, but first let's take a look at arrays in memory. So this is the basic principle here. So when we want to create an array, it's the array is of type T. It and let's say we call that array A, and we designate its length to be L. And so this is when we declare an array like this, you basically have C allocates a contiguous region of memory for us. And contiguous basically means that all these blocks are right next to each other in memory. So that's why we're able to do pointer arithmetic by, let's say, getting the pointer to A and adding 1 to it. And that gets us the next element because it's right next to it in memory. And so we have, so this allocates a region of L times the size of T bytes because there's L items and each item is size of T big, and T is the actual item or the data type. So we have to multiply by the number of items, and that's how much memory is allocated for an array when you create it. So if you have an array of characters, you have the first pointer here, and it goes all the way up to here. And then let's say you have an integer array of 5 elements. You could basically add 4 because an integer is 4 bytes in memory. And so you could add 4 to get to the next element. And similar concepts for double and storing an array of strings. And yeah, so now we know that the identifier A can be used as a pointer to the 0th element, which is this. And these are basically different ways to, let's say we have an array called val. We can basically do all these different types of operations to access different parts of the memory. So if we just did val plus 1, that basically just takes the pointer x and adds 4 to it, and then it points here. But if we did star val plus 1, what we're actually doing is taking the pointer and pointing it here, which is at x plus 4, and then dereferencing that, and that gets us the value 5. But you guys already know this stuff. This is stuff we covered in the beginning. And so let's say we create 3 arrays here, right? And so these are 3 arrays. And let's say all of these arrays are contiguously located in memory. So each element is 4 bytes apart because this starts at 16, ends at 36. And then this starts at 36, ends at 56. And then the next one starts at 56. And don't worry about the type def and all that here. Basically what this is saying is zip dig is equivalent to saying the whole, to declaring it like this. And so they were, these example arrays were created contiguously, but this isn't always guaranteed to happen. So if we wanted to access an element from this array in C, we would just do it like this. We would have a function get digit. We would pass in the array. We'd pass in the index that we want. Let's say we want digit 0. We just do Z and then pass in 0 here, and we'll get the first digit. And well, I have, for each of these examples I'll show you for how to get the element, I also have the assembly version. But I mean, we don't really need to go over the assembly because I basically just want to get the point across for how arrays are stored and accessed. But I guess I could talk about this piece of assembly here. So let's say RDI contains the pointer to Z, and RSI contains the digit, which is the index that we want, then this is the instruction that'll get us the value. So what we're doing is we're taking the actual digit, and we are gonna multiply it by 4, right? So when we multiply the index by 4, that means let's say you want to get to index 2 here, right? This is the element at index 2. We're multiplying it by 4 because that's how many actual bytes in memory we want to move. And and then yeah, so we multiply by 4 because that's how many bytes we want to move. And then RDI contains the starting point, and we just let's say we want to get to this index, then it'll be 2 times 4, which is 8, plus RDI. So 16 is what's in RDI. So we do 16 plus 8 and we get to 24. And then if we dereference that, we'll get this element at index 2. So that's how this instruction works. It basically just does 4 times RSI, adds RDI, and moves that into EAX, or which is the RAX return register. And so that's the value that'll be returned. Wait, okay. And then let's say we have multi-dimensional or nested arrays, which means basically 2-dimensional arrays or something like that. So if it's R rows and C columns, they'll be arranged in row major ordering. And what that means is first row 0 will be stored in memory, and then row 1 will be stored, then row 2 left to right. So basically we have row 0 here, which because this first index corresponds to the row, and then we have row 1, and then all the way until row R minus 1, right? Which is, and R is the number of rows. And the size of this array is going to be the number of rows times the number of columns times k bytes, where k is the number of bytes that the element stored in here takes up. So, and yeah, so that's how you calculate the size of this array. And so basically, the R times C tells us how many elements are there, right? So if we have 5 rows, 6 columns, we have 5 times 6, 30 elements. And then you also need to account for how many bytes each element takes up. So if each element takes up k bytes, we just take that 30 multiplied by k. Let's say it takes up 4 bytes because it's an integer array, then it'll be 4 times 30, which is 120 bytes. And okay, and then we have yeah, so this is basically just a depiction of the row major ordering we were talking about. So let's say there's an array that looks like this. This is what it would look like in memory. It would store the first row, then the second row, then the third, then the fourth. And that's how the computer will store them. And then let's say we want to get to a specific row in this array, right? To do that, what we'll need to do is start at A, and we need to add some amount to it, right, to get to the next row. So so here we can see that okay, so we're gonna say that this this array is of integers, so each integer takes up 4 bytes. And so for however many columns there are here, 1, and then as many, and then C columns, we need to multiply 4 by C, right? Because in each row there are C elements. So when we do 4 times C, we'll get the number of elements in the row. And then we need to add when we do A plus 4C, that gets us to the end of the row, right? And if we want to get to a specific row, we also need to multiply by the row that we want to get to. So if we want to get to row I, we need to do the 4C And then 4c is the number of elements in one row. And then to traverse I rows, or to go through I rows, we also need to multiply that 4c by I and add that to A. And that's what'll get us to whichever row we want to get to. And yeah, so this is basically just an example of that. So we have this array called PGH, and if there are 5 columns, as we can see, and each column takes up 4 bytes, we do PGH plus I times 5 times 4, and that'll get us to where we want. And this is the corresponding assembly code for doing that. And I'll post these slides and you guys could go through it, but it's the comments explained it pretty well, exactly what's going on here. And so that's how accessing an element or a row in this 2D array would be done in assembly. And so yeah, so next up we have if we want to access a specific element in a specific row. So if that's what we want to do, we need to do A plus I times C times 4. Because so we discussed how to get to a specific row, right? We do A plus I times C times 4. And if we want to get to a specific element in that row, what we need to do is we need to add that many more bytes, right? So let's say we're at the beginning of this row now, and we want to get to this element ij. So we are at A at I, but then we also want to go over j more places. And to get to j, what we need to do is add 4 times j, because each element in between will take up 4 bytes. So what we're going to be doing is adding 4j, and that'll get us to our desired element. And this is basically to get this formula over here, what they did is they factored out the 4. And so it just becomes 4 times, or I times c plus j, and then the whole thing multiplied by 4 when you factor out the 4. And then if we have this nested array, this is just an example of how what we just talked about here would be done in assembly. It's basically, it's a pretty, if you look through this on your own, you'll be able to understand it. But I don't think I can go over it right now because there's other things to cover. And yeah, so that's basically how that would work. And I have this little helpful guide here if you want to understand this assembly code. Okay, and then so there's 2 ways we could store these arrays, right? What we could do is, I am actually not single, as someone asked in the chat. It's all right. Yeah, so let's say we have an array that stores pointers. So a 2D array, there's 2 ways of storing it. It could either be stored contiguously like it was before, or what we could do is we could have another array that stores pointers to each of the specific arrays, right? So let's say we have another array univ, and this stores a pointer to this array, this stores a pointer to this array, and this one stores a pointer to this array. Then to get to it, what we can do is okay, so in C we would just do this, right? But what's actually happening underneath in assembly is we need to take the value at where univ starts, and we need to add 8 bytes times the index we want to go to, because each pointer takes up 8 bytes. And once we go there, we will get to whichever array we want to. And then from there, we'll add 4 times j bytes to get to our desired element. And so you're probably wondering why we just went through all of this. And so basically, this is the reason that we did this. And so if we have so basically to store a 2D array, we could either store it this way or this way, as a nested array, which we had before, which you saw was the row major ordering, right? Or we could have it as we could store arrays like this, which means that we would have another array that stores pointers to the 3 arrays, and we could access any element that way. And so we have the address computations of doing both of these actually look very different. So for one of them, we get to a specific location in memory, and then we dereference that. But here, we get to a specific location in memory, dereference that, and then we actually have to dereference that whole thing, as we just saw. And this results in 2 dereferences, and this results in 1 dereference. And this is obviously going to be a better choice because this results in 1 dereference rather than 2. But the thing is, we don't always have a contiguous amount of memory to allocate, right? So although this is ideally faster, this isn't always what's going to happen because we don't always have a contiguous amount of memory, like enough space to give to one array that needs to be stored. So what we do is we store each row in a different place, and then we'll just have another array that stores the pointers. And although it results in 2 dereferences, which makes performance a little slower, it does allow us to store more things because we could store it in different places in memory. So when you're coding, I guess you could kind of make this choice yourself based on how many elements you have. So if you have like a bunch of elements, you probably want to go this way because you probably won't be able to find a contiguous block. But if you don't have that many, you could store them contiguously. And so what's happening here? She actually doesn't go to Rutgers, so I'm not sure how you'll be able to meet her, but yeah. So we have, next we'll talk about structs in memory. And so, okay, so we have, so we just talked about how arrays are stored, right? But structs are actually stored pretty differently than arrays. And okay, where was I? The chat is a little distracting right now. So we have, let's say we have this struct, right? We have an integer array called A. It stores 4 elements, and we have another variable which is of size t, and then we have a struct which stores the next element. So in memory, this would be stored like this. We would first store this array. It would be 16 bytes long because 4 elements times the size of int, which will be 4. So it'll be 4 times 4, 16. And then let's say size t is 8. And so that's where I will be stored. And the next struct will be stored from 24 to 32. And or the pointer to the next struct, because the pointer to the next struct will only be 8 bytes. We're not actually storing the entire struct here, so that'll be 8 more bytes. And yeah, so basically, so yeah, when we store a struct, we need to make sure that we have enough space in memory to store it contiguously. And wait. Um, yeah, there aren't many people in today's recitation, which I guess that's a good thing because um, I guess they could find this stuff in the recording maybe. Um, can we have a dynamically allocated array in a struct? Uh, yeah, I guess you could have a dynamically allocated array because it would kind of, wouldn't that kind of just result in a linked list though? So it wouldn't actually be a traditional array. Um, yeah, so the next thing we have is, well, let's talk about how structs are actually stored in memory, right? So let's say we have this struct here, right? It stores a character C, it stores an integer array called I, and it stores a double called V, and and so basically this is how you'd expect it to be stored, right? It stores a character which is 1 byte long, then it stores an integer array um, which would take up 8 bytes because it would be I0 would take up 4 bytes and then I1 would take up another 4 bytes. And then we have this double V, which would be 8 bytes long. So it'll basically be 17 bytes, right? But the thing is, if you went into C, created this struct, and then tried to get the size of S1, it wouldn't actually give us 17 bytes. And so that's a little surprising, right? So basically how it's stored is things are aligned in a specific way in memory. So if you store a struct, the primitive data types all require k bytes, right? Which is how big k corresponding to how big that data type is, and each address must be a multiple of k. So this is the condition that allows us to not be able to store the data like this. So if we store a character, that's fine. So a character could be stored anywhere, right? But yeah. So but the next thing is um, we have we have to store an integer, and to store an integer is 4 bytes, right? Which so k here it would be 4. The address has to be a multiple of 4 wherever the integer starts. So that means that these 3 bytes would result in wasted space, and p plus 4 would be the multiple, would be the place in memory where the first integer would start, and then p plus 8 will be the second place, the second portion of memory where the second integer will start, and then at this point we'll be at p plus 12, right? This is where p plus 12 is, and then we want to store something that's 8 bytes long, right? Which is our double. But then again, 12 is not a multiple of 8. Yeah, 8 is not a multiple of 12, which means, oh, sorry, 12 is not a multiple of 8, which means that we'll have to start at 16, and we have another 4 bytes of wasted space. And so the actual size of the struct in memory will be 24 bytes, not 17 bytes. And yeah, and this is done because just the way memory is accessed, it's very particular, and it's for performance reasons. And so that's why this wasted space is there. So there's actually there's another overall requirement that we need to satisfy, and that is um, that each structure has the alignment requirement k, where k is the largest alignment of any element. So the initial address and the structure length has to be a multiple of k. So that means um, when we store this struct, so what would be our k here for this struct? We know that the k would be 8 because what's the biggest element in the struct? It's the double. So because the double is the biggest, our k is 8, and that means where our struct end has to be a multiple of 8. So the struct ends at p plus 24, and this is a multiple of 8, so we're good, and that's why the struct is stored this way. And so let's see. Yeah, exactly. So Eric got it right on point. So the best way to then store these things is to store the largest element first. And so putting the largest data types first allows us to waste the least amount of space. So in this example, if we store the character, then the int, then the character, what happens is we store the character, waste 3 whole bytes, store an int, and then we store the other character, waste another 3 bytes, right? Because the next thing that gets stored has to be at another multiple. So but when we store the largest data types first, we'll have the int I and then the character and then the next character. So here only 2 bytes are wasted as opposed to 6. And you can see why this would be important. So let's say we have an array of structs, right? It's not just one struct. If we have an array of like 100 structs, then storing it this way would waste 600 bytes, whereas storing it this way would store 200 bytes. So that saves us a whole 400 bytes. And yeah, so that's basically how we could save space by making good design choices when we code. And so next we'll talk about locality. And then, so this is the principle of locality. So programs tend to use data. And so basically programs tend to use the same things over and over again is what it's saying. So things near an address or things, or these exact same thing that we had before. So there's this concept of temporal locality, which means that recently referenced items are likely to be referenced again. So that same item is likely to be referenced again in the future. If you have a variable, it's likely that it will again be referenced. And then we have spatial locality, which means that nearby addresses are likely to be referenced. So if we have an array, then elements near, so let's say we start an array at index 0, the elements near that, 1, 2, all of those are likely to be accessed again. And so we could use this concept to design a system where we could avoid talking to main memory more than we need to, because talking to main memory is an expensive task, and we want to do that as little as we can. So here's just an example. So in this piece of code here, let's say we have a sum starting at 0 and then a for loop, which runs from 0 to n, and we just add up, and then we have an array A. We just add up all the elements of A and return the sum. So referencing the array elements in succession is a form of spatial locality because the elements are all around each other, and they're referencing the sum variable each time we do the addition, and also when we return is an example of temporal locality. And so this is for the data references in this piece of code, but if we also look at the instruction references, the actual instructions in sequence are a form of spatial locality. So when we access this instruction, it's likely that we'll go to this one again, which is the next instruction in the sequence. And then we cycle through this loop repeatedly. This specific loop happens to go over happens to continue n times. So that's a form of temporal locality because we're accessing the same thing, the same loop over and over again. And so that is what brings us to cache. And so basically, remember we saw that diagram? We've added another piece into the diagram, which is the cache. And cache memories are, we talked about how they're SRAM based, and they're very small. what they do is they hold frequently accessed blocks of main memory. So the CPU doesn't have to keep going back to the main memory for everything that it wants to access. It could have something stored close by. It's not a lot of storage, but the CPU, we can design systems um, so that things that will likely be used will be stored in the cache, and the CPU will be able to access them much quicker, speeding up runtime by a lot. Because going to memory is expensive and going to the cache is is a much cheaper operation. And so what the CPU does is it first looks for the data in the cache, and then it goes over to the main memory instead of going straight to the main memory. And so now what we have is, this is just basically a fundamental idea about caches, but what we want to focus is on, the big idea here. So so the memory hierarchy has a large pool of storage. And so what we want to do is we want to keep data that is accessed more recently near the top of the storage, because the top is faster access. As we go farther from the CPU, the access time increases, and we want to store more commonly used data at the top of the pyramid, which is, as we saw, at the cache level is right. So we have the CPU, then the registers, and the cache, and the cache is the closest place where we could store stuff. And so now let's just go over some general concepts about caches. And so they're basically smaller, more expensive, a subset of the memory. And then so what we have is, wait one second. Okay, yeah, so it's less expensive to access, but that's not what this is referring to. But yeah, so data is transferred from, so in memory, we have blocks of memory, right? So we have block 0 through 15. And if we access, let's say block 10 from the CPU, it will store block 10 in the cache, because it thinks that block 10 will be accessed again later on, so that when it looks for some piece of data again, and it happens to be stored in block 10, it'll be faster to access it. So let's say we have, okay, so let's talk about the concept of a hit. So if the CPU requests 14 and it finds 14 in the cache, or block 14 in memory, and it happens to find that block in the cache, then that is what we call a hit, because it was able to find the block that we needed. And then when that doesn't happen, that's what we call a miss. So if there's a miss, then let's say we request 12 from the CPU. 12 is not there initially, right? So it's a miss. And what we do is go and request 12 then from the memory rather than the cache. And we get it from the memory, bring it back to the CPU. But before we give it to the CPU, we decide to come back and store it here into the cache, because we think that it'll be needed again later on. And so there's different placement policies which determine exactly where a block will be stored in the cache. And there's different replacement policies which basically talk about which block will get evicted to store this new block, because we don't have unlimited space in the cache, right? Let's say we have 16 blocks here, we only have 4 blocks here. We can only store 4 blocks at a time. So we need to get rid of another block in order to store this 12. So there's this 9 here, we got rid of it, and we stored 12 here instead. But this concept of what block needs to be replaced, that's called a replacement policy. And we'll talk more about both placement policies and replacement policies as we go on, but there's different types of replacement policies, such as first in, first out, and or a least recently used replacement policy, where the least recently used thing gets evicted. And first in, first out is self-explanatory. And so these are the general caching concepts. And so we could have what's called a cold miss, and a cold miss just occurs when the cache is completely empty. We start out nothing in the cache, so of course it'll be a cold miss. And so when the cache is empty and a program begins to run and the cache is empty, what we call that is warming up the cache, because initially the cache is empty and we're putting things in there, so we're warming it up, because once it's warmed up, we will be able to access things from the cache more time, so there will be less misses. And then we have what's called a conflict miss, and a conflict miss is it occurs when the same exact block, so let's say 2 blocks of memory are mapped to the same location in the cache, right? So if block 0 and block 8 are both mapped to the same location in the cache, so let's say we want to go and access block 0, right? We'll go into memory, get block 0, put it in the cache. And then we want to access block 8. We'll go into memory, get block 8, because it's not in the cache, because 0 is stored. 0 is the only thing stored. And then we go and get 8. And let's say 8 maps to the same place that 0 was. So the 0 gets evicted, we put 8 into the cache. And then let's say we want to go get 0 again. Then the 0 that we had in the cache is no longer there because it got replaced by 8. So we need to go back to main memory, get the 0, and then we store the 0, but let's say we want 8 again. Then we need to go back to main memory, get the 8, and this is a conflict miss. So both things are stored at the exact same position, and if 2 things need to be accessed right after the other many times, it would basically mess up how the cache works, because the same thing needs to be accessed, and we'll keep having to go back to main memory even though we keep caching it. And then we have a capacity miss where the number of blocks that we need is larger than the cache, so we just won't be able to store everything that we need in the cache, and because the capacity is full, we'll have a lot more misses because the cache isn't big enough to store all the things that we need. So let's say we need 5 things or 10 things, and our cache is only 4 blocks big. And if we do like a first in, first out replacement policy, we'll keep getting rid of the 4 things and putting 4 new things in. But let's say we need those old 4 things again, we'll have to go back to main memory and stuff. So if we keep needing to access the same 10 things again, but we only have space to store 4 things, that's basically going to be a bunch of capacity misses, because we don't have enough space to store all of those things in the cache. And yeah, so that's basically all of today's presentation. And so yeah, that's all I have for today. And yeah, if you guys have any questions, you can ask now. And I'll stop the recording here. And I'll stop sharing first, and I'll stop the recording, and it'll be up by probably in like an hour. And yeah, I'll see you guys next time.